Hello, linear algebra students. We're going to go over this test 1 from spring 2021. This test came from a different professor, but it is a wonderful part of our studying for our first test. I will just say that I changed a few questions to better fit the material we covered. It's a great practice. So here we go. The first question, we're given a matrix A as 3 rows and 4 columns. We want to determine the reduced row echelon form of A. Here I have recopied matrix A, and I'm going to label all of my row operations. This is part of showing our work. The first thing I'm going to do is try to get zeros underneath this first 1. So we can take -2 row 1, add that to row 2, and at the same time take row 1 and add it to row 3. In the second row, I have 0, I have 4 minus 6, I have 10 minus 12, and then I have 2 minus 4. And in the last row, well, I'm just adding row 1 to row 3. So I have 0, 2, 2, and -2. At this point, I already see where my next leading 1 will be. It's going to be in the 2, 2 position. So let's take -1/2 times row 2, and everything else I will just keep the same. Row 2 will become a row of all 1s, and then I will be ready for my next step. Now move down. We have the leading 1. Let's make a 0 underneath. So we take -2 row 2 and add that to row 3. The only row that changes here is row 3. You see, we have all zeros and -4. At this point, I see where my third leading 1 will be. It's in the row 3, column 4. Take -1/4 times row 3. You notice I am in row echelon form right here. In fact, this matrix is also in row echelon form, but the question asks for reduced row echelon form. And really, I have 2 more steps. Let me highlight my leading 1s because now I have found them. I want to make zeros above my leading 1s. And let's do that now. We can take minus row 3, add that to row 2, and then take -2 row 3, add that to row 1. And perhaps I will write the matrix on the next line. We get zeros here. And then we have one more step. We can take -3 row 2, add that to row 1, and we will be in reduced row echelon form. So this one becomes 0, and then we have 6 minus 3, which is 3. So this is my answer here to letter A. This matrix is in reduced row echelon form, and it is the reduced row echelon form of A. Now let's move on and use it. The next question, we want to determine all solutions to AX equals 0 in parametric form. Well, typically, if we have, say, AX equals B, and we want to find all solutions, we would augment, right? Do A augmented with B and perform the very same kind of operations we just did. However, in this case, if you augment with 0, that column will always stay 0 under all of these row operations. So I can just read it off from this. Imagine I have a bunch of equals 0 over here. We can see the free variable. Maybe I'll copy and paste my reduced row echelon form on the next part. We have one free variable, x3. We can call that, say, t. And then if you imagine equals 0 on augmented, we would have x4 is 0. We would have x2, well, it would be minus t, and we would have x1 is minus 3t. So let's put our answer in parametric vector form. x1 is -3t, x2 is -t, x3 is t, and x4 is 0. This would be our answer here. All solutions to AX equals 0 have this form. We have one free variable. And maybe I will label this as such. x3 equals t, is our free variable. This is my final answer on number 2. The next question is kind of a short one. We are given the row echelon form of some matrix M. Note that this is not reduced row echelon form, but immediately we can see here is where we would have, say, leading 1 in our reduced row echelon form, or you could call it a pivot position in, say, the row echelon form. It's here, here, and here. Okay, there's 3 of them. And immediately we can write down the rank. The rank is 3. Next question. Does the linear system mx equals b have a solution for every b in R3? Explain the reason. The answer is yes, because every row, and I will state it in terms of the reduced row echelon form of M, will have a leading 1. And so, well, this linear system is never inconsistent. For example, we would never see 0, 0, 0, 0 augmented with C, with C non-zero in a row echelon form for this matrix, not with a leading 1 in every row. Now the third part, how many free variables do we have? Well, the free variables correspond to the columns where I've not highlighted a pivot position. You can see it's labeled, we have 8 columns. We have 3 pivot positions. And so the answer here is 8 minus 3, which is 5. This is my answer here. And this is my answer here. Number 3, L is a line in R3 spanned by this vector W, which is 1, 2, 3. We want to decompose Y into its projection along the line or onto the line, orthogonal projection, plus the component of Y, which is perpendicular to the line. And so let's compute the projection first. The formula for projection along a line of vector Y would be Y dot W divided by W dot W. This is the scalar, and then times vector W. This is what we want. So what we really need here is we need to compute 2 dot products, and then that will be what we put in front of vector W as the coefficient. Okay, Y dot W. Well, we have 1 times 2 plus 1 times 2 plus 3 times 8. Altogether, this is what? 24 and 4, we get 28. And W dot W, now I'm dotting W with itself. We have 1 squared plus 2 squared plus 3 squared. This is 9 plus 4 plus 1. This is 14. So the ratio, you see 28 over 14 is 2. So this projection is just 2W, which I can write. If we take 2 times vector W, we get 2, 4, 6. 2, 4, 6. This is the first part. The second part of this question, letter 2. Well, we want the component of Y, which is orthogonal. This is just Y minus the projection. Well, we see Y here, it's 218, and then we subtract off 246, and this is vector subtraction, which is component-wise. We get 0, -3, and 2. 0, -3, and 2. This is the component of Y, which is perpendicular to the line, like this. Now, third part, if you take this component dotted with W, what do we get? Well, W was the vector 1, 2, 3. Okay, it's right here, you can see it. So I'm dotting 1, 2, 3 with the vector 0, -3, 2. I get 1 times 0 plus 2 times -3 plus 3 times 2. You see, 6 and minus 6, I get 0, which is exactly what I wanted in this question. So this was number 3. Let's move on. Now we are doing some questions involving linear transformations. And the first one is a question, is this map a linear transformation from R2 to R2, explain the reason. No, I can see it very quickly because, for example, if we take T of 0, 0 here, evaluate at 0, 0, we get 3, 0, but this is not equal to 0, 0. That is one thing that absolutely must hold for linear transformations, that 0 maps to 0 because, well, you can either see it through properties or we know there is some matrix A such that T of X is AX. And A times the 0 vector is always 0. Therefore, T of 0 must be 0 if you have a linear transformation, and it is not here. So the answer is no. This is my reason that T of 0 is not equal to 0. Well, now in number 5 and in number 6, we have two maps that are linear transformations, and we are asked to find the matrix. So here, number 5 is a composition of two maps. So I'll find the matrices for each one, and then I will just multiply. Let's see, T1 of E1. This one takes in a vector in R2 and gives you a vector in R3. T1 of E1 is 0, 1, 0. E1 has a, in R2, E1 is this, right? Has a 1 in the first coordinate and zeros everywhere else. And T1 of E2, well, here the X is 0 and the Y is 1. We get 0, minus 1, 3. 0, minus 1, 3. And so the matrix for T1, well, you put T of E1 as the first column, T of E2 as the second column. We get this. This is for T1. Now over here, let's do the matrix for T2. T2 is projection onto, orthogonal projection onto the line y equals minus x. So I can write this line as the span of, well, if x is 1, y is negative 1, for example. And then the matrix here for our T2, we take 1 over W1 squared plus W2 squared. We read this off this vector, if this vector is, say, W1, W2. And then we have W1 squared here, W2 squared here, and then multiply W1 times W2, W1 times W2. Altogether, we can pull this inside. The coefficient is just a half. So this matrix is a half minus a half minus a half, a half, 1/2. And this is a 1/2. And then minus a half and minus a half. And one thing I've mentioned in class that you definitely want to check is you should have the columns of the projection matrix are on your line. If you don't, you've made a mistake somewhere. And we see that here. Both the columns satisfy y equals minus x. Well, now to get the transformation for the composition, this is what I actually asked for in the question. We want to do T2 and then T1, the matrix. So we put this one first. This is happening first. So it's going to go on this side. And then this happens. Of course, if you tried to go in the other order in this example, you couldn't. You could not compose, say, first do T1 and then do T2. You can't because, for example, if you think matrices, this is 3 by 2. This is 2 by 2. Everything is wonderful. If you try to do it in the other order, it wouldn't work. You would have, say, a 2 by 2 and a 3 by 2, right? You cannot make that matrix product. This was 3 by 2. This was 2 by 2. My matrix will be 3 by 2. And let's calculate it. We have some options here. Certainly, I think row dot column, we will have a first row of zeros because the first row of this matrix is 0. Now, if you take this row, you take a half plus a half, we get 1. Take this row, we get negative a half minus a half, we have negative 1. And then finally, you take this row, we have negative 3 halves and then we would have positive 3/2. So this is my final answer here. This is what I will put a box around. Number 6. This is a properties question. We had one like this, very similar to this on a worksheet. And then we also use some properties on our problem set. But this is a properties question. So we are given T of this vector, and we are given T of this vector, and we want to find the matrix. Well, we already know the first column because it's just T of E1. Here's the first column of my matrix, but I'm going to have to do just a little bit of work to get the other column. So let us note that this, which is E2, equals, let's see, it is this vector, which is 2, 1, minus 2 times this vector, which is 1, 0. Now this means if I want T of this vector 0, 1, which is my E2, well, this is a linear transformation. And so I can just break this across the sum. This will be T of this one, 2, 1. And then we have minus 2 T of, well, this is E1, but I will write it as 1, 0. Now, this one, T of 2, 1, that is V, and T of V is 3, 4, 5. So T of 2, 1 is 3, 4, 5. Then we have minus 2. T of 1, 0 is 1, 1, 1. And here we're going to calculate T of E2. This equals, we have 3 minus 2, we have 4 minus 2, and 5 minus 2. So now let's write down the matrix of this transformation. The first column, T of E1, which is given. And the second column, we had to do a little bit of work to get and use properties. This is 1, 2, 3. So this is my matrix. This was a properties question, and a fantastic one at that. This is my final answer here. Now let's move on. Number 7. We want to find the inverse of the matrix A. Write down all of our work. Of course, always we write down all of our work. How we find the inverse of a matrix? And this one won't be too bad. Well, we start off with A, which is 1, 2, 3, 2, 5, 7, 2, 4, 7. And then we augment with the identity. Here it's the 3 by 3 identity. What I want to do is perform elementary row operations just like I did in the first problem until I get to identity something. And this something will be the inverse of the matrix. So let's do this now. What I want to do here, make zeros. I'm trying to get the identity on the left-hand side. So let's take minus 2, row 1, add it to row 2. At the same time, minus 2, row 1, add it to row 3. Row 1, I have not changed. Row 2, we have 0. We have 5 minus 4. We have 7 minus 6. And then we have negative 2 here. 1, 0. Okay, this is row 2. Now for row 3, we have 0. We have 0. And then 7 minus 6, and there's a minus 2 here, 0, 1. This was our first step, but you see how nice this was? Just in one step, I have this. So maybe we can do a few fewer row operations than we did in the first problem. Now, I have my leading ones. I need to get zeros above this one and get 0 above here. So it looks like 2 more steps. This first step, I will take minus row 3, add it to row 2. And then I will take minus 3 row 3, add it to row 1. And the main thing you need to be careful about is you have to do it on the whole augmented matrix. On the left-hand side, there's not that much that changes. In fact, all of this, 1, 2, 0, 1 remains the same. I just have a 0 here and a 0 here. But now on the right-hand side, we have to be a little bit more careful. Minus row 3, add it to row 2. We have 0, we have 1, and negative 1. Then we have minus 3 row 3, add it to row 1. So this will be 7. This will be 0, and this will be minus 3. You see, I just have one more step. I need to make this 0, and then I will have the identity on the left-hand side. So let's take minus 2, row 2, add it to row 1. The left-hand side, all that changes is we get a 0 here, but I have to be careful on the right-hand side. Right-hand side, minus 2, row 2, added to row 1. I have this 7, I have negative 2, and then I have negative 1. We have arrived because you see here, this is the 3 by 3 identity. And so immediately we know the inverse of A inverse. In fact, I will just copy it from this here. It's this. This is the inverse. Copy and paste. We have the inverse of our matrix A. We move on. The second part of this, we're going to find all solutions to AX equals B, or B equals 1, 2, 0. Well, it says all solutions, but A is invertible. So we will have exactly one solution. We should know that, or we do know that from our theory. In fact, how do we get the solution? Well, you can multiply on both sides of the equation by A inverse. And we will get, let's write it, that X is A inverse times vector B. So let's write this. We have calculated A inverse. It's right here. I want to take this matrix and multiply by 1, 2, 0. When I multiply this matrix times this vector, let's see, if we do row dot column, I get 7 minus 4, which is 3. The next one, I get 0 plus 2 plus 0, which is 2. And the final entry, I have minus 2 plus 0 plus 0, which is minus 2. So this is my final answer here. This is all solutions. In fact, it's just one. We have a unique solution. And this is the vector here. The last part of this question says, does a to the 6th times x equals b have a unique solution for any b in R3? Explain the reason. Yes, without a doubt. The answer is yes. So what's the reason here? Well, as let's say a is invertible, certainly it is. We found its inverse. As a is invertible, then any power of a is invertible. So in particular, a to the 6th is invertible. And moreover, a to the 6th inverse equals a inverse to the 6th. So if I needed to solve this, the solution, unique solution, would just be here, a inverse to the 6th power times vector b. This gives me my unique solution here. This is the explanation. The answer is yes. And we have justified my solution is x equals a inverse to the 6th times b. But any power of an invertible matrix is certainly invertible. You have a product of invertible matrices, it will be invertible. This is what we're using here. This is our solution. Now, number 8, this is the last question. This is true, false. So I'm going to give a reason. It says reason not required, but I'm trying to educate and not just solve the test myself. So we will fill out the whole lower part of this page with our reason. Okay, don't worry. But let's understand what's happening here, because the hypotheses are going to help us answer true or false. throughout this, we are working with square matrices. Square matrices. Great. The first one says T of x equals a squared plus b times x defines a linear transformation T from Rn to Rn. This one is true. Well, I don't know how much explanation there is here, but maybe I'll just say for number 1 down below, I will say that a squared plus b is defined, and this is an n by n matrix. And so this is using the definition of linear transformation, that there is some matrix such that the transformation evaluated at x is just the matrix times x. The second one, if ax equals b has a unique solution, then ax equals c has a unique solution for any c in Rn. This one is also true because we have to think about invertibility here. So if we want to explain number 2, ax equals b has a unique solution. This says, so we know here in this example, well, we have a square matrix, and we know for some b, ax equals b has a unique solution. This would say the rank has to be n in this example, and this happens if and only if, well, the reduced row echelon form is the identity, or A is invertible. These are all different ways to say that. And in particular, A is invertible, we will have that ax equals c has a unique solution. So this is one way to think about number 2. The solution would be just A inverse times c, like this. Number 3, it says if a to the 4th is A, then A cubed is the identity. This is definitely false. Let's understand why. One thing I focused on in class is you cannot cancel off when you have matrix multiplication. Definitely not. And that's kind of what this is saying. Can you cancel off one of the A's on each side and conclude that A cubed is the identity? The answer is no, you can't do that. If A is invertible, no problem. Multiply on both sides of this equation by A inverse, and you will get A cubed is the identity. But there is no hypothesis here that A is an invertible matrix. So what would be an example like this? Let's take, I was going to do a projection matrix as an example, because if you project and you project again, you get yourself back. So projection matrices satisfy, say, A squared is A, and in particular, you would have A to the 4th is A. But an even easier example that just came to mind, let's take this. Take the all zero matrix. Then certainly A squared, or A to the 4th, is A, because it's a zero matrix. So that is even simpler of an example than one of the projection matrices. Here's false. It's false. You cannot switch the order, but let's actually write this out. What is A plus B squared? If you have n by n matrices, you can certainly do this. A plus B will be an n by n matrix, and you can multiply it by itself. But you have to understand this is A plus B times A plus B. Now, this is A squared plus we would have outer plus we would have inner plus we would have last. Okay, and there's no reason that A and B must commute. They're just n by n matrices. So this is, if A and B do not commute, and we saw many examples of that, say from class, if A and B do not commute, then AB plus BA is not equal to 2AB. And then we have an issue with this formula in number 4. That was a false statement. Number 5, fifth one, V and W and Rn, they are two solutions to Ax equals B, where B is a non-zero vector. The statement says V plus W is a solution, and we have to decide if it's true or false. This one is also false. Okay, so here's the hypotheses. I'm going to scroll up. Let's see if we can still see it. Oh, a little bit. Maybe I'll make this a little smaller so we can see the hypotheses as we write. Hypotheses are, for number 5, our hypotheses are that AV equals B and AW equals B, but B is not equal to 0. Well, this is a properties question. If you want to consider A of V plus W, this would be AB plus AW, which is 2B, B plus B, which is 2B, which B is non-zero. And anytime B is non-zero, this will not be equal to B. So that is how we see that 5 is false. Now we have one more in our true false. It says if the rank of AB squared is n, then matrices A and B are both invertible. Well, this is true. This is true. We can think about it just in terms of invertibility, which is fine. Rank of AB squared is n. That is equivalent to AB squared is invertible. Now, the question is, how can I get A invertible and B invertible from this? AB squared is invertible. So let's let, say, M equal this, AB squared inverse. I'm just calling it M because it's going to make my life easier. So in particular, I know AB squared M is the identity, n by n. And if I multiply in the other order, M AB squared is the identity. How can I get that A and B are invertible? All I need to do is just group here. So look, like this. So now look, I have a product. This is an n by n matrix, and A is an n by n matrix. I have a product of two matrices giving me the identity. This was one characterization of being invertible. So here, immediately from this, we see A is invertible. In fact, its inverse would be B squared times M. Now this one I just need to group slightly differently. Maybe I will draw one arrow. I can write B squared as B times B. So this is M, A, B, B is the identity. And now I can group this side, here and here. Now you see MAB is an n by n matrix, and this times this n by n matrix is the identity. Therefore, this gives us that B is invertible. This does. We get B is invertible, and in fact, its inverse is MAB. This was realizing 6 was true, just thinking about invertibility. You can also make an argument about rank. I think I mentioned, which we will actually discuss later in chapter 3, that the rank of a product is less than or equal to the rank of the pieces, but the product has full rank. And so necessarily A would have to be rank n, and B squared would have to be rank n. And from that you could get that B must also be rank n, which would imply both matrices are invertible. But I didn't use that here. I just use this criterion for invertibility. That all you need is one n by n matrix, and multiply on one side, get the identity. This means you're invertible, and that this matrix is the inverse. And I did that for both A and B. So 6 was a little bit challenging, but I also think it was great for us to think about. 6 was true. Well, this is the end of this previous exam, and I hope this video has been beneficial for you. Good luck, students, on the test.